the AP problem. This is about the reaction of, here it comes, there we go, N2O4 as a gas, and the equilibrium that has with 2NO2 as a gas. Now I know it shows you the structure here, but you should be able to get the same information by looking at obviously what the structures are. So here's what we get. It says predict the delta H for the reaction, justify your answer. Okay, so how do we predict what the delta H is going to be with no numbers given to us and no information given to us as like part of the problem, as like the delta H formation for N2O2 or N2O4 or NO2 or any of that. So how do we just predict what's going on? So here's what's going on. When we break bonds, break bonds equals energy absorbed. Okay? Form bonds equals energy given off. That's as simple as I can put it. So in this case here, the reason why they gave you the structure is so that you could identify what's going on. Are we breaking bonds or are we forming bonds? And clearly, here is a bond between N and N, nitrogen and nitrogen, and when it breaks apart like this, you have to put energy into the system. So that would be energy going into the system, which means endothermic, which means a delta H that is positive. Okay, a positive delta H. I know that's like a big stretch of like all of these different things, but when we break bonds, you have to put energy into breaking the bond, just like you have to put energy into breaking a pencil or into breaking something else, a concrete block with a sledgehammer. You have to put energy into that. Okay, but forming bonds is different though. Forming bonds gives off energy or the bond wouldn't form. Okay, the whole thing is at a lower state of energy when a bond forms, after it forms, than before. If it wouldn't be in a lower state of energy, then of course the bond wouldn't form, and we have that happening all over the place. So predict the sign of delta H. That would be a positive delta H, okay, for the reasons I just gave. Predict the sign of the delta S for the reaction. Justify your answer. Again, we need to look to see what's going on here to identify. Notice that we have one particle here, but on this side here, I have more than one particle. When I increase the number of particles, I increase my delta S. Okay, let me say that one more time. Here I have one particle on the left-hand side, and then my product on the right-hand side is two particles. When I increase the number of particles, I increase the amount of randomness. Okay, so over here my delta S increases, which means, of course, I have a plus delta S. Okay, so let's move on knowing that much information. So increase in temperature increases delta S, increase in volume increases delta S, increase in number of particles increases delta S. So all those things increase delta S or randomness. It says one of the diagrams below best represents the relationship between delta G, the temperature for the reaction given part, and assume that delta H and delta S are independent of temperature. So that means that draw a circle around the correct graph, explain why you chose that graph in terms of the relationship of delta G, delta H, and delta S. Okay? So here we're looking at this specifically, this equation specifically. Notice that if we increase temperature, okay, as we are for each one of these graphs, we're increasing temperature as we go. The delta S and the delta H are independent, which means not changing. So the only thing that's changing, here I have and if you give numbers to it, sometimes it helps. My 100 kilojoules delta H, this is my delta H term. Okay, so let's see what happens to delta G. Excuse me. I have a minus, and then I have, let's just do 298, and that's going to be times. Now 100 joules for delta S is reasonable, which means that it's 0.1 kilojoules, okay, per Kelvin, like this. So what happens if I increase the temperature term? So right now, I have 100 minus, that would be what? 29.8. Okay, so that is what? 70.2 kilojoules. Not that it matters, but what if I do a higher temperature? Notice that the delta H doesn't change and my delta S won't change. What if I do 400? Okay, 400 means 40. So if this is 400, that's an H. I don't know what the heck I'm doing here. Okay. Let me try this one more time here. So that's 29.8 equals 70.2. This means that I'm going to do 400 times 0.1 because the delta S doesn't change. And then I need more room, which means 100 minus 40, bonehead, like that, equals 60. What's going on? I went from 70.2 at 298 to 60 at 400. Okay, that means my delta G is decreasing as my temperature increases. So which one of these then up here shows delta G decreasing as temperature increasing? So as temperature increases this way, this would be the one that shows my delta G decreasing. Okay, so that is the answer. Okay, let's see if we can, I know I'm over my time, 6 minutes, but I just want to, let's see if we can push through some of this. Reaction and mixture of NO2 and N2O4 and NO2 is at equilibrium. Heat is added to a mixture. Now here's what we know for I. It says explain why the concentration of NO2 decreases. Explain why the concentration of N2O4 decreases. N2O4 decreases because if I have a delta H, a positive delta H, that means that when I increase temperature, increase pushes it more to the right. Okay? In other words, that means endothermic, my heat then is used like a reactant, and when I increase a reactant on this side, it pushes the whole reaction to go more towards the products, which means that the concentration of N2O4 goes down. Okay, that's number one. So, and that's all because we decided that it was a positive delta H. This says the value of K equilibrium is 5.0 times 10 to the negative third. Okay, well the value of at 100 degrees increase, is it greater or less than or equal to this value? So when we increase the temperature, what happens? When we increase the temperature, we get more product. More product means that we're going to increase the K value. So the K value is going to increase because if you guys remember, the K value for this would be NO2 in our concentration, like that. And if the top is what increases, then the whole fraction increases, which means that the K will increase. Okay, so letter C, 1 and 2 are answered there. D, using the value of K at 25 degrees, predict whether the delta H is expected to be greater than, less than, or equal to the value of the T delta S. So as we're looking at this, because this is an endothermic reaction, the higher temperatures that will go further to the right. That means that the K value will be greater than, okay, we already talked about that, sorry. So we're just talking about the K at 25 degrees Celsius is less than 1. Okay, it was what, 3.5 times 10 to the negative 3, or whatever it was, 5 point whatever, times 10 to the negative 3. The whole point is this right here. If it's less than 1, that means that my amount of NO2 squared is less than N2O4. Okay. So that means that the delta G, now see if you can, if you can follow along with this. So if this term is less than this term, that means that my delta G is positive. This is a non-spontaneous because my K is less than 1, okay? And the only way that you can get a positive delta G is when you have a higher delta H than you do the T delta S term. So this must be higher than this term here. Must be higher. That's the only way it can happen. So that means that delta H, when we answer this question, is it greater than, less than, or equal to the value? It must be greater than for my delta G to be positive. My delta G is positive because my K value, my equilibrium constant, is less than 1, which means that the reactants, there's more reactants than there are products, which makes this a non-spontaneous reaction. Okay, thanks for paying attention.